Before moving on from section 4.6, we want to kind of highlight one of the key features of this variation of parameters is that this method can actually be extended to higher order equations. So we kind of derived the basic idea by looking at a first order linear ODE. We generalized it by being able to find a process to find a U1 and a U2 to help us solve second order linear ODEs. But it also can be extended to solve general nth order linear ODEs. It would start off by doing the same thing. You would begin by solving the homogeneous differential equation where this right-hand side would be set equal to 0. That would give us our complementary solution. Again, if it's of order n, then we would believe that y sub c, the auxiliary equation that's associated to it, would be a polynomial of degree n, so they would have n roots over the complex numbers, and therefore we would get n complementary subpieces here. So the complementary solution would look like c1y1 plus c2y2 plus ... up to cn With that complementary solution, we would do the same kind of thing. We would now want to move on to finding the particular solution, and we would replace these constants with functions of x. So we would believe that the particular solution would have the form u1 y1 plus u2 y2 plus ... all the way up to un yn. And if you go back and rewatch the video when I derived the 2x2 system by hand, it's going to take quite a bit of work. Because now to solve for y sub p, we need to solve for now n functions. So we need u1 through un. So this is going to produce a n by n system. So we have n equations now in n variables. Those n variables being u1 prime, u2 prime, u3 prime, all the way down to un prime. Okay. Via symmetry, though, there's kind of a niceness in all of these that the uk prime term, so to find the u prime k function for k equals 1 to n, we take the Wronskian wk, the sub-Wronskian wk, and divide it by w. Again, that comes from Cramer's rule. In the 3x3 case, you can kind of see what it would look like. u1 prime would be equal to w1 divided by w. u2 prime would be equal to w2 divided by w. u3 prime would be w3 divided by w. In the 2x2 case, we just kind of memorized these. w1 turned out to be, I believe it was negative y2 times f. w2 turned out to be y1 times f. But in general, those came from also determinant matrices. Here we have 3x3 matrices, and you can kind of look and see what it is. But you can use that idea to solve. And again, most of the time, especially as we move into higher order, you won't always, unless you're looking at some very restricted cases, get these functions in higher order systems that are actually going to be integrable. A lot of times with these higher order systems, more often than not, the u's that you get oftentimes end up being represented in integral format. Okay. So that finishes section 4.6. The last thing in chapter 4 that we're going to look at is a very special type of linear differential equation, which is called a Koichi-Euler differential equation. Okay. What makes a Cauchy-Euler equation kind of special, if you will, is that we have the terms in front of the derivatives. So the nth derivative will be accompanied by a function that is an nth power of x, of course with constants as well. So if we have like a second derivative, it'll be paired with an x squared term in front. A first derivative would be paired with an x term in front, like this, and then the function itself would be compared with a constant term. Okay. So these numbers, the an through a zeros, are constants, and this gives us what we call now a Cauchy-Euler equation. Okay. As an example of this, we can see kind of very quickly if we had like ax squared, second derivative of y with respect to x, plus bx times the first derivative of y with respect to x, plus cy times 0. This would be a second order Cauchy-Euler differential equation. We can solve these, so the methods for solving these would follow very similar to our variation of parameters. We can do that, but these can also be solved a little more quickly as well. And the method of solution we would try for this would be to try to do the substitution y equals x to the m. And also, just one comment. If you remember back really early in the class about existence of solutions, we would need for this lead coefficient to not be 0. So remember, you need the a sub n of x coefficient to not be 0. Well, this coefficient will always be 0 at precisely x equal to 0. So these solutions that we'll be finding throughout section 4.7 will be defined on the interval I, where I is the largest interval that does not contain the number 0. And so it's either going to be on the interval 0 to infinity or negative infinity to 0, which is where our solutions are going to exist. Let's see what happens. So let's suppose we have a kth order derivative here. And let's suppose the solution is of the form x to the m. Okay. Well, we can plug this in. For example, if we look at a second differential equation here, the second derivative of this would be m times m minus 1. And then we would get x to the m minus 2. We would plug this in here. So we have a m minus 1. We would have an x to the m minus 2. But then when you multiply by the x squared, maybe I should write that part, because they don't really do a super good job of explicitly showing all the algebra here. Let me write a little bit more so you can get some more details here. So again, let's suppose for a minute that we have ax squared d squared y dx squared plus bx dy dx plus cy equals 0. We're going to assume a solution of the form y equals x to the m. For this one, I would need my first two derivatives. So dy dx would be m x to the m minus 1. The second derivative would be m minus 1, and then minus 1 will give us an m minus 2. If we substitute these into the differential equation, we're going to get an ax squared times m minus 1 x to the m minus 2 plus bx times m x to the m minus 1 plus c times x to the m equal to 0. And now these are the coefficients. We have an a m minus 1, and when you multiply by like bases, we add the exponents. So that ends up being x to the m minus 2 plus 2 is just x to the m. Plus here we have a b times m, which is bm. X to the first times x to the m minus 1. That's m minus 1 plus 1, which again gives us x to the m. Plus cx to the m equals to 0. We can factor out from all of this the x to the m. It's a common factor. And then this presents us with what we call the new auxiliary equation. It's am times m minus 1 plus bm plus c. It was a second order linear differential equation, so it's not surprising that if I expand this all out, that we're going to get a second order or a quadratic equation for the auxiliary variable m. And if we're able to go ahead and solve these, then the solutions for m we see will correspond to our powers of x. There will be solutions to this differential equation. The first case that we're going to consider is what happens when this auxiliary equation has two distinct roots. And just to save myself some writings, let me go back and refer to the text one more time. But this is the first case we're going to encounter. Case 1, when the auxiliary equation has two distinct real roots, let's call them m1 and m2, then we get the complementary solution will be formed by c1. It's going to be x to the m1 plus c2 x to the m2. So this is our first situation, distinct real roots. The solutions for m end up being the exponents of the x variable. Let's go ahead and solve this. So the first one we have is x squared d squared y dx squared, second derivative, minus 2x dy dx minus 4y equals to 0. This is a second order linear differential equation, and notice that it is a Koichi Euler equation because the powers of x match the corresponding derivatives. So because of that, we're going to assume that we have a solution of the form y equals x to the m. To save some writing, we know what y prime is. That's going to be m x to the m minus 1. Y double prime would be m minus 1 x to the m minus 2. And now let's go ahead and plug that into our differential equation. So we have x squared times the second derivative. That's m minus 1 x to the m minus 2 minus 2x times the first derivative. That's m x to the m minus 1 minus 4 times the function y. That's x to the m equals to 0. We have m times m minus 1. Multiplying those like terms together gives us x to the m. Minus, we have a 2m here. X times x to the m minus 1 will give us x to the m. Minus 4x to the m equals to 0. We can factor out the x to the m. And this gives us our auxiliary equation. So m times m minus 1 times 2m minus 4 would be equal to 0. That is m squared minus m minus 2m minus 4 equals to 0. M squared minus 3m minus 4 equals to 0. This factors as m minus 4 times m plus 1 equals to 0. And so we get two distinct real roots. We get m equals to 4 and m equals to negative 1. Therefore, the solution, the complementary solution, which is this is a homogeneous solution. Excuse me, it is a homogeneous ODE. Therefore, the solution in general is going to be c1 x to the m1 plus c2 x to the m2 because we had distinct real roots. So our solution is c1 x to the fourth plus c2 x to the negative first power. It's very easy to check this one if you wanted to. You could go ahead and verify that this is the solution to the ODE, but it's pretty straightforward.